Usually when we talk about high stakes on this show, we're talking about, I don't know, a massive tech merger or maybe a shift in the global economy. But today,
Today is different.
we are talking about the absolute highest stakes possible. We are talking about the leading cause of cancer-related death worldwide.
Lung cancer.
Lung cancer. And we know, thanks to decades of research, that screening works. Low-dose CT screening specifically.
It catches things early. It saves lives.
But there is a massive bottleneck, a huge one. We have the technology to scan people. We have the machines, but we're struggling to teach our computers how to read those scans effectively.
And that right there is where today's deep dive comes in. We are just looking at a medical study today. We're looking at the fuel required to train artificial intelligence to actually help doctors save those lives.
And our source for this is a paper from Radiology, Artificial Intelligence, published in 2025 by Aviva J. Wang and a team from Duke University.
The title is The Duke Lung Cancer Screening Dataset, DLCS for short.
And I know, Dataset sounds a little, well, let's be honest, it sounds like homework.
It sounds dry, so dry, but I promise you it's not.
It really isn't, because what they've built here is basically a blueprint for how we solve this massive problem in modern medicine, a problem they call data starvation.
Which is such a fascinating concept, right? In AI, we often think the problem is the algorithm, the code itself.
We need smarter robots.
Yeah, we need a better robot.
Yeah.
But usually the code is fine. The problem is that the AI is, well, it's hungry. It needs thousands, maybe millions of examples to learn what a lung nodule looks like versus, say, a normal blood vessel.
See, this is the part that always confuses me. You'd think, hey, hospitals have millions of scans, right?
They do.
They are doing these scans every single day. Just feed them to the computer. Why is that so hard?
It's because of the ground truth problem. An AI doesn't know a spot is a nodule just by looking. It needs a teacher. It needs a human expert to draw a little red circle around the spot and say, this, right here, this is the bad thing.
Exactly, annotation. And hospitals have the images, but they don't have the red circles.
Okay, but we have had data sets before, right? I mean, people have been working on this for years. Why do we need a new one from Duke?
Because the old ones are. They're dinosaurs.
Dinosaurs.
Imagine trying to train a self-driving car, but the only maps you give it are from 2005.
The roads have changed, the signs are different, maybe the traffic laws are even updated.
And the cameras are different. That is the state of so many medical data sets. The big ones researchers use,
Yeah.
like LIDC-IDRI or NLST, they're ancient in tech years. I mean, we're talking over a decade old.
So the CT scanners they use to build those old databases are not what doctors are using today.
Not even close. CT tech has advanced so rapidly. Modern scanners produce much thinner slices.
Okay, hang on, explain that. Slice thickness. Why does that matter to a computer?
So think of a CT scan like a flipbook.
Okay.
If you have thick slices, it's like a flipbook where you're missing every third page. The motion is jerky, the details are blurry.
I see.
Modern scanners give you a smooth, high-definition flipbook. So if you train an AI on that blurry, jerky version from 2010, and then you ask it to diagnose a patient using a high-res scan from 2025, it struggles. The whole texture of the data is completely different.
So we have a data starvation problem because the food we have is stale.
Stale and scarce. Because again, to make new, fresh data, you need radiologists to sit down and manually draw boxes around every single suspicious spot. And radiologists are, well, they're expensive, busy people.
They have patients to treat.
Exactly. They can't spend 40 hours a week drawing boxes for a research project.
So enter the Duke team. They decided to build a better mousetrap, or I guess a better data set. And they realized they couldn't just use brute force. They needed a hack.
A workflow hack. They call it a semi-automated pipeline.
Okay, before we get into the geeky how, which I definitely want to do, let's just talk about the scope of what they built. We were looking at data from between January 2015 and June 2021.
So a very contemporary window.
And the numbers are huge. I mean, they curated 2,061 annotated screening thoracic CT scans.
And within those scans,
They identified and annotated 3,187 specific lung nodules.
that volume is critical. But what strikes me even more than the raw numbers is the nature of the data. This isn't a clean laboratory data set where everything is perfect.
Right.
This is retrospective, real-world clinical data from a high-volume center.
Which means it includes all the messiness of actual hospital life.
Yes, it reflects the variety of patients you actually see in a waiting room, not just some curated subset that looks good for a study.
And speaking of the waiting room, I want to highlight something that really jumped out at me in Table 1 of the paper. We talk a lot about bias in AI, like facial recognition not working on darker skin tones.
Because the training data was all white guys. It's a huge ongoing issue in tech.
Well, historically, medical data sets have had the exact same problem. They were often built from populations that weren't very diverse. But look at this demographic breakdown. The mean age is 66.7, which makes sense. But the gender split.
It's almost exactly 50-50. 1,032 females, 1,029 males.
And the race and ethnicity breakdown, this is the headline for me. 23.1% of the patients in this data set are Black or African American.
That is a crucial detail. Many older data sets just severely underrepresented minority populations. If you train a cancer-spotting AI only on scans from white patients, there's a risk, a very real scientific risk, that it might miss things in others.
Or gets confused by just, normal anatomical variations.
Right. So by deliberately ensuring this data set represents the actual population of Durham, North Carolina, which is diverse, the Duke team is helping build tools that work for everyone.
It's equity through better data.
You can't fix the algorithm if the input is biased. You have to fix the input first.
Okay, so we have the, massive, modern, diverse data set, but the how is where the ingenuity really shines. They didn't just lock a bunch of med students in a room for 5 years and say, start drawing boxes.
No, that would have been impossible given the scale. They used this semi-automated pipeline.
This is the secret sauce. It wasn't just humans, and it wasn't just AI.
It was a tag team.
A tag team. I like that.
Think of it like a funnel. They started with the raw images. Then, they used an existing AI tool, specifically a detection algorithm from the MOAI framework, to take a first pass.
MONAI.
Medical Open Network for AI.
Yeah.
It's an open source set of tools. They used a pre-trained model to act as a scout.
A scout, okay. So it scans the images and looks for things that might be nodules.
Exactly. It says, hey, I found something here, here, and here. Now, usually, a human would have to check all of those.
Right. Tedious.
But Duke did something really clever. They used the text reports from the doctors who originally read the scans back in, 2015, 2016.
So they taught the computer to read the doctor's notes.
That's it, natural language processing. And they categorized the findings into 4 groups. This is really the brilliance of their workflow in Figure 2. Group 1 is the easy wins.
The slam dunks.
In Group 1, the AI scout found a nodule, gave it a high probability score. At the same time, the system checked the doctor's report, and the doctor also mentioned a nodule in that exact spot.
So the AI sees a spot, and the notes say, spot found on slice 40, and they match up.
And because they match, the researcher said, we trust this. They used the AI's box, no new drawing needed.
Okay, what percentage of the cases was that?
That was 72% of the cases.
Wow. So nearly 3/4 of the work was just done automatically by verifying the AI against the old paperwork.
Pretty much. Then you have Group 2, the second look. Here the AI found something, but maybe it wasn't super confident. It gave it a lower score.
Okay.
However, the location still matched the doctor's report.
So the system says, I'm not sure, but Dr. Smith said there's something here, so I'm going to trust Dr. Smith.
That's it. The human weak label, the text report, overrode the AI's hesitation. That accounted for another 14% of the cases.
So right there, between Group 1 and Group 2, you have, 86% of the nodules being identified largely by the machine, guided by a text report.
Which is massive for efficiency. It solves that burnout problem we were talking about.
But what about when the robot fails? I mean, AI isn't perfect.
It's not. And that's Group 3 and Group 4. Group 3 were low-scoring candidates that a medical student had to manually check and say, yep, that's real. But Group 4, that is the real manual labor.
The AI missed it completely.
Either the AI missed it, or it was a complex shape, or something the algorithm just hadn't seen before. In these cases, only about 9% of the total, a human, had to go in and draw the bounding box from scratch.
But think about that difference. Instead of drawing boxes for 100% of the cases, the humans only had to do the heavy lifting for 9%.
And that is the takeaway. This study proves you can build massive, high-quality data sets without burning out your radiologists. They annotated over 3,000 nodules, and the vast majority were done with this human-in-the-loop assistance.
Human in the loop? I feel like that's the phrase of the decade. It's not AI replacing us, it's AI prepping the ingredients so we can cook the meal faster.
A perfect analogy. But there is another layer to this data set that makes it so valuable. Something beyond just the images in the boxes.
You mean the context?
The context. You're talking about Lung-RADS.
Lung-RADS, right. Stands for Lung CT Screening Reporting and Data System.
Which sounds incredibly bureaucratic.
It does, but it's vital.
It is. It's the standardized scoring system doctors use to categorize how suspicious a nodule looks. It ranges from 1, which is negative, to 4, which is very suspicious.
So it's not just here is a lump, it's here is a lump, and a trained doctor rated it a 4A, which implies a certain level of danger.
Exactly. And this data set includes those Lung-RADS scores. This gives the AI what we call ground truth context. It teaches the AI not just to find a shape, but to understand how a trained human expert interpreted that shape.
So it's adding the doctor's intuition, or the doctor's training, into the data itself. But here is where it gets really interesting for me, because this data goes up to 2021.
And we're looking at it now.
So we know what happened to these people.
This is the retrospective advantage. The researchers could look at the electronic health records and essentially see the future. They know which of these patients actually went on to develop lung cancer.
Yeah, I have the numbers here. Out of the 2,061 scans, 155 patients, so about 7.5%, were eventually diagnosed with lung cancer.
And that transforms the data set from a simple collection of pictures into a prognostic tool.
Right, because now you can train an AI to look at a scan from year 1 and say, hey, human doctors might rate this a 2, but I've seen 10,000 cases like this, and in 2 years, this turns into adenocarcinoma.
Precisely. And speaking of which, that was the most common type they found, about 43% of the cancers, followed by squamous cell carcinoma. By having the specific cancer type and the timing of the diagnosis linked to the original image, you can find patterns that are invisible to the human eye.
That is the aha moment. It's not just finding the nodule, it's predicting the timeline.
I do want to pump the brakes for a second. We can just say this is the magic bullet. As with any scientific study, there are limitations, and the authors are very transparent about them.
Okay, yeah, let's play devil's advocate. They relied so heavily on the old text reports. Doesn't that mean they are just baking in the old mistakes?
That is the biggest limitation. It's called inter-reader variability.
Which is a very polite way of saying doctors disagree sometimes.
Or doctors miss things. If the original doctor, back in 2017, missed a nodule and didn't write about it in the report, the software wouldn't look for it. And if the AI scout also missed it...
that nodule is just gone. It's not in the data set.
Correct. So the data set is only as good as what was reported, not necessarily every single thing that existed.
And what about the Lung-RADS versions? You mentioned they used V1.0 and V1.1.
Right. And medicine evolves. We're on newer versions of Lung-RADS now. The definitions of what counts as a suspicious nodule have shifted a bit. This data is locked in the past standards.
So if you train an AI on this, you are training it to think like a doctor from 2017.
Correct. Which is still incredibly valuable, but it's a nuance researchers have to be aware of. Also, regarding the sizing, computers are very literal.
What do you mean by that?
Well, when the AI draws a box around a nodule, it might include a tiny bit of a blood vessel next to it, or it might cut off a fuzzy edge that a human would have included. The paper mentioned the algorithm sometimes over- or underestimated the size.
Did they check their work on that?
They did. They had a fellowship-trained cardiothoracic radiologist spot-check random samples from each of the 4 groups. And the semi-automated method was accurate between 97 and 100% of the time in those samples.
Okay, that's pretty reassuring.
It is. It shows the method is robust, even if it's not absolutely perfect.
So let's zoom out. Why should our listener, who might not be a radiologist or an AI engineer, care about this data set? Why does this matter to the average person?
For several reasons. First, the whole philosophy of open science. They didn't hoard this data. They made the images, the annotations, everything publicly available.
That's huge. Usually big institutions keep their data locked up. This lets a kid in a dorm room or a startup in a garage access world-class medical data to test their ideas.
It levels the playing field. It serves as a benchmark or reference data set. If you invent a new cancer spotting algorithm, you can test it on the DLCS data to prove it works.
But I feel like there's an even bigger picture here with the method.
That is the most exciting part for me. This paper is a blueprint. Think about how many other diseases are diagnosed using images.
Brain tumors on MRI, liver lesions, fractures on X-rays.
Millions of them. And hospitals have archives just full of these images and the text reports that go with them. The method Duke used here can be applied to almost any of those.
So they've basically written the instruction manual for unlocking all that frozen data trapped in hospital servers?
Exactly. We have been complaining about data starvation for years. This paper shows that the food was there all along. We just needed a better can opener.
That is a powerful image. It feels like we are on the cusp of a flood of new, high-quality data because of methods like this.
We are, and that data is what will power the next generation of diagnostic tools.
So to recap what we've unpacked today, the Duke lung cancer screening dataset is a major step forward. It bridges that gap between old, dusty data and the needs of modern AI.
It uses a clever, semi-automated process that AI and human tag team to annotate thousands of nodules with incredible efficiency.
And it includes the vital clinical context, who the patients are, that they're diverse, and what happened to them, the outcomes.
Which allows us to train AI not just to see, but maybe even to predict.
And it's all open source. It's a gift to the scientific community.
A gift that will likely save lives.
Absolutely. Now, here is a thought I want to leave you with. We spent a lot of time talking about this hybrid model, humans using AI to verify AI. And we often have this fear of AI replacing doctors, right? Of the cold machine taking over.
It's the most common anxiety I hear.
But this study shows that the most powerful model isn't the machine alone, and it's not the human alone. It's the cyborg, basically, the human-machine team.
The sum is greater than the parts.
Exactly.
Okay.
So if we can apply this semi-automated curation to every organ in the body, if we can unleash this on the liver, the brain, the pancreas, what other silent diagnoses are sitting in hospital archives right now?
What patterns are hiding in plain sight?
Right. What cures are just waiting for a smart algorithm and a curious human to connect the dots? The data is already there. We just have to start listening to it.
The answers are in the archive.
And thanks to papers like this, we have the keys to open the door. Thanks for listening to this deep dive. Go learn something new today.
Stay curious.